Okay, well, let me introduce Nancy Levenson. She's going to be telling us about dusty tori, and of course I have to introduce you very politely as Nancy's the incoming Deputy Director for Gemini, so I have to be as nice as I can to you. So,
that's right. I'm learning. I'm developing a lot of friends since I have something to do with director's discretionary time starting in the summer. But of course, it's really a pleasure for me, Jose Miguel, to be back here. I really enjoyed the 3 months that I had spent at the IAC at the beginning of the year, and was so sorry to leave that I needed an excuse to come back. So this is it, and this is just great. So I will be talking mostly about dusty surroundings of AGN, active galactic nuclei, but I will point out that a lot of the modeling that I'm talking about is absolutely relevant to any energy source that might be heating some surrounding dust. So even if you're interested in stars, then that should be relevant for you. So this is work that I'm doing largely in collaboration with Los Piratas, who are the CanariCam AGN science team, and much credit goes to them, and you'll see many of their names throughout. So just a little bit of very brief motivation about why you might want to study AGN, at least if you might be interested in galaxies or stars. And it really goes back to the M-sigma relationship between the masses of black holes and the stellar velocity dispersion. And so that says that something about the black holes and the stellar growth together are fundamental to galaxies. All galaxies with bulges seem to have these supermassive black holes in their centers, and they scale together. The AGN feedback itself, something about the outflow processes, may be shaping the surroundings and ultimately change the star formation processes. And so, so one of the ideas for the sort of cosmic downsizing really attributes that to the AGN. So the black hole grows largely through accretion of new material. So that says that the AGN phase is important to galaxy growth, even though overall it's not the dominant phase of the life of a galaxy. So all of that is a bit of motivation for studying AGN, at least if you're a little bit interested in galaxies. If you're only concerned with the solar system, I'm not quite sure what I can tell you, except for when I get to talking about the dust, and I think that'll be relevant there. Also, one thing I want to say is that the AGN accretion process seems to be related to the obscuration, and some of the issues that we just heard about with the liners are also relevant for the sort of normal luminosity AGN. So here's the cartoon view, the very familiar cartoon view of AGN unification. And the idea is to say that the central engine of these beasts really is the same thing, the accreting supermassive black hole, but we wind up having a wide variety of observational consequences because of this optically and geometrically thick of torus of material around that accreting black hole. And really one of the biggest differences is whether we are able to see directly down to the clouds that are very close to the black hole, moving very rapidly, producing spectrally broad lines. And so we do get good views of that broad line region in what we call the type 1 AGN, whereas in some cases we're stuck looking through this optically thick torus of material, cannot see those broad optical lines, and those are the type 2s. What we'll be looking for in the mid-infrared is we actually get to see the emission of the obscurer. So the dust in this torus reprocesses the intrinsic AGN light, so that intrinsically hard continuum winds up emerging at longer wavelengths and really peaks in the mid-infrared. So most of what we're seeing is thermal dust emission. And I'll point out, this is an example actually of a ULIRG, but it's a Spitzer spectrum, which gives us nice broad wavelength coverage. And from Almudena, we saw several examples like this. That some of the spectral features that we'll be looking for are, especially around 10 microns, we'll be looking for the silicate, which may appear at absorption or emission, but also the polycyclic aromatic hydrocarbons, the PAHs, so that really appear throughout this band pass. And so a number of examples of relatively strong PAHs there. So as I said, I'm very interested myself in AGN, but of course stars can also heat the surrounding dust. And so to give you some examples of some of the types of models that I'm looking at, these are 3 different dust heating spectra. So the AGN spectrum, the broken power law shown there in the black line, as I said, relatively hard spectrum. But we could also compare that, say, to a starburst spectrum shown with the red line, or even, a little bit unfairly, to just an A0 star spectrum. And the unfair part here with the A0 star is that I have scaled it to the luminosity of the starburst and the AGN. But all that's really important is that you put the dust close to the heating source. And as long as the dust is close to the heating source, the exact hardness of the spectrum doesn't really matter. So the dust emission is ultimately going to not depend at all on the heating spectrum. And just to demonstrate that quantitatively, so for these 3 different colors showing 3 different intrinsic heating spectra, what I've got now in the models, the different line styles are now representing different optical depths. And this is a relatively simple distribution of a smooth spherical shell of dusty material around the heating source. And so we go from an optically thin case shown in the solid line there. So optically thin, we wind up getting to see that hot optically thin dust surface. And so the 10 micron silicate peak shows up strongly in emission, and also the 18 micron silicate peak strongly in emission for that optically thin. But you'll see almost no difference for the different heating spectra. Again, as long as the dust is close to the spectrum, it just reprocesses the light, and what matters is the properties of the dust itself. And so that's why these spectra all wind up looking the same. The other line styles are now going for larger optical depths. And so optical depth, where here I'm defining it tau V, optical depth in the V band. So the dashed line here is tau V of 100. We start to see some absorption in the 10 micron silicate feature, and the dotted line, tau V of 200, now getting to very deep absorption. And you also notice some differences out toward the longer wavelengths. So again, the big point there is it doesn't matter what you did to heat the dust. And the downside, if you're interested in understanding AGN or even your starburst or something like that, is you're not going to get that by looking at the dust emission. But the good news is you'll learn an awful lot about the dust, and specifically the geometry of the dust distribution. So now even refining the cartoon view a little bit more to really emphasize just this torus. So in this cross-section view, it's this optically and geometrically thick, dusty torus that's reprocessing the intrinsic emission that's emerging in the infrared. Now, I will point out in this sort of classical view of an AGN torus that I've drawn it to be very smooth or homogeneous. And so there are a few consequences for us thinking about the mid-infrared emission here. The first, so the big difference between these type 1 and type 2 views, this direct type 1 view where you get to not only see the central engine without any obscuration, but you get to see this extremely hot surface on the inner throat of the torus. And so a couple of consequences for that are, first of all, that there's extremely anisotropic mid-infrared emission. There's an enormous difference between getting to see that hot surface that's emitting very strongly compared with the type 2 view where you're looking through the large optical depth, the large cold optical depth. And so in this kind of smooth torus, the type 1s emit much more strongly than the type 2s in the mid-infrared. And then there are also big consequences for the silicate emission. The type 1s, because you see this hot optically thin surface, you would see strong silicate emission, whereas the type 2s looking through the cold material, you would see deep silicate absorption. And so these are some models from Pure and Krolik showing just that. So the different, these are different views from actually a not very not very face-on view, a sort of a 40-degree angle view down to the throat of the torus where you see the silicate emission, the 10 micron silicate emission, and then enormous differences, order of magnitude differences in the total flux that emerges depending on viewing angle because of this. So I should point out the tau that they're using there now is the Thomson optical depth. So column densities of 10 to the 24 is a tau equals 1 in these particular models. So this is an optically thick torus, a truly optically thick torus. Yeah, just different scales. Everybody defines their taus at a different wavelength. Yeah. So those are theoretical predictions of consequences for these smooth tori, and the problem is that that's just not what we observe. So in general, with observations of the 10-micron silicate, we generally observe weak features, both in emission and in absorption. So we don't see the very deep absorption of the type 2s, and we tend not to see strong emission, although there are cases certainly of type 1 AGN that show silicate emission. But it's overall very weak. Overall, we find nearly isotropic mid-infrared emission, no strong differences between the type 1s and type 2s. There's a lot of fine-tuning of these torus parameters to describe the spectral energy distributions over broad wavelengths with these smooth models. And really, part of what's happening is that temperature winds up being a strict function of radius. The hot material is close into the AGN. The cold material is farther away. And so what that means is that you need an extremely large torus to produce mid and far infrared emission. You need cool dust. And that doesn't seem to agree with what we observe. So some of my colleagues at the University of Kentucky have been developing inhomogeneous or clumpy torus models. And the idea here is that now, instead of having the dust smoothly distributed around the AGN, we've got individual optically thick clouds, so individual optical depths, say tau b greater than 20. And the idea is that the AGN can directly heat some clouds. So some cloud surfaces are exposed to the AGN, but others are hidden. And so those hidden clouds will only be heated by the ambient radiation of the reprocessed light from these directly heated clouds. And so the computations do account for full radiative transfer within the dusty clouds, and they also account for the angular dependence of the emission. And so some of the just general principles that follow here are that temperature and radius are now no longer simply related. It's possible to have relatively cool clouds close to the AGN as long as they're blocked. It's possible to have relatively hot clouds farther away as long as they have, such as this one, as long as they have a direct view. And as an observer, you wind up collecting a mix of these illuminated and dark faces from all types of AGN, from type 1s and 2s. And also something I'll illustrate later, that this type 1 or type 2 classification winds up not being a monotonic function of viewing angle. And so here's another way to think about looking more generally at this clumpy torus model. So we've got the heating central engine and some distribution of clouds, and that's what's now important. And so the big thing the models define is the cloud distribution. So here I've got a description of the number as a function of radius and angle beta, where it measures beta from the equator. And so it depends on n naught, the number of clouds along an equatorial ray. It depends on beta, this height parameter. And sigma here is essentially describing the thickness of the torus. So a large value of sigma says it's a very thick torus with covering large solid angle, whereas a low value of sigma says it's mostly confined to the equatorial plane. And then the clouds are distributed as a power law in radius, so Q is just the parameter that describes that power. And the clouds go from the dust sublimation radius RD out to some outer radius, and so that's another scale parameter. And then we wind up computing from all viewing angles the reprocessed emission over a large wavelength range. And so here's some examples now of as we've applied these types of models to some observations. This is work led by Rachel Mason, starting with NGC 1068. So the 11-micron image that you're looking at, this was taken at Gemini North using Michel. So first of all, you can see very extended emission, and most of the extended emission we associate with the narrow line region of NGC 1068, not with the torus itself. And we've got some other information from maser observations to tell us about the alignment of the torus roughly east-west, and also, therefore, because the masers are observed, that we have a nearly edge-on view here. So much of the extended emission is the narrow line region, but the torus itself is extremely, extremely compact. And so really, just to reiterate on Dana's point from before, spatial resolution is terribly important. If we want to diagnose the torus, we need to make measurements on very small scales. And so what we're looking at here are from different spatial regions, extracting different regions along the slit from the spectra in the N-band window. So here's the peak emission, and so you can see this shape with a relatively strong rise towards the shorter wavelengths, and compare it with a couple of the off-peak steps that really show different spectral shapes. So again, just to emphasize, we want small spatial scale if what we're trying to measure is the torus. Another way to look at that, the thick black line here is now the peak spectral extraction that we had made. The other points shown in red are other measurements made on small spatial scales. And you can see, first of all, that the overall shape of the spectral energy distribution is very different if you make the measurements on large spatial scales. So what we're interested in is the small scale to diagnose what's happening with the torus. And so we wound up using these sort of clumpy models, and we were fitting just the 10-micron spectrum. And in fact, because at the time that we started doing this, we had some problems with our silicate calculations, we didn't even use the whole shape of the silicate spectral feature. We're just basically looking at some flux ratios in depth. And so those models 1, 2, and 3 shown with the solid lines show that there are a range of different models that can basically accommodate what we observe through the N-band. And one thing I'll point out here is that we were not fitting the broader spectral energy distribution, and I'm almost surprised at what a good job we did with describing some of those other measurements, because they really didn't go into the fits at all. So by making these comparisons with the models, what we ultimately are trying to do is determine the distribution of those clouds, the distribution of those dusty clouds. We also wind up recovering the intrinsic AGN luminosity, which isn't such a big deal if you're thinking about the type 1 AGN, where there are lots of good ways to measure that. But especially if you're thinking, for example, about Compton-Thick AGN, of which 1068 is an extreme example, that these models wind up providing us with some way to recover that. Overall, and that's not just with this particular example, but looking also at some small samples of various Seyfert galaxies, we generally find small numbers of clouds along equatorial rays. So this N-naught parameter tends to be less than about 6. And I'll just point out that that's consistent with some of the observations of X-ray variability showing changes in column density. So just a word about the silicate features. In general, the clumpy models produce weak silicate features, both in emission and in absorption, and that really just goes back to being able to observe both those hot and cold cloud faces together. It's the mix of those things that softens the features. And just to give an example, of the other people have raised this issue, because I guess my argument is getting through that this is one of my little pet peeves, but to be careful about apparent optical depth and its relationship to actual optical depth along the line of sight. And so for our NGC 1068 example, the apparent optical depth through the silicate feature is an apparent optical depth of 0.3, but if we consider the total distribution of clouds, then the model optical depth at 10 microns that we find is greater than 10. So the silicate feature is not a great way to determine the total amount of material. Not simply. Not simply. No, because it really just depends on the total distribution of clouds. I'm sorry. I wish I had a nice, I bet if I could give you some nice relationship that everybody would quote that, we'd all be happy. But no, it's not that easy. Yeah, unfortunately. So another point is, as I had said before, that this type 1 or type 2 classification may arise from any viewing angle, and it simply depends on whether or not you happen to run into a cloud. And so if you happen to run into a cloud, then the object would be classified as type 2. And so here, even from a relatively pole-on viewing angle, in this fake example, if you run into a cloud, it would be classified as a type 2, whereas from a more equatorial viewing angle, if you just happen to avoid all clouds along the line of sight, then it would be classified as a type 1. Something else that's not directly, that's not exactly this point, but that both emission and absorption in the silicate feature are possible from both types of AGN. It simply depends on whether you see more of those hot illuminated faces or more of the cold faces. And so this is a rather interesting example, and this is, again, work led by Rachel Mason that's just been published. In the Seyfert 2 galaxy, NGC 2110, we do observe silicate emission. So it's a type 2, large line of sight optical depth overall, but because we get to see more of those hot cloud faces, we see the silicate emission, and that arises both on small scales with these gray points, a spectrum that we used Michelle and Gemini to get, but also on larger spatial scales in this case. So the darker line is the Spitzer IRS spectrum. So in this case, applying the models, we find that we can indeed produce silicate emission from the obscured view. And in this case, it tends to be a relatively thin torus, that scale height sigma being just 15 degrees. But the viewing angle is nearly equatorial, a viewing angle of 80 degrees. One of the other things that we find now is we clearly have a problem with the dust composition. And so the model 1 shown in blue here, that's formally the best fit of the model. But you can see that we're really missing the peak wavelength of the emission. And this model 4 that I'm showing is a contrasting example, is just to illustrate that this kind of edge-on torus view can give us the silicate emission, but we wind up predicting the wrong peak wavelength. And so again, that's why I say that I think what we're seeing here is that this type of distribution of clouds can be a type 2 and give us silicate emission, but we need to be using the right dust to really match the silicate feature in detail, and that's what we're not doing right now. So just a few comments on some outstanding issues. Now, there's a lot of degeneracy in the model parameters because basically there are lots of different ways you can mix the clouds to produce the mid-infrared spectra that we observe. For example, suppose the important physical property is just the clouds that are close to the heating source, there are different combinations of the parameters that you could use to achieve that. You could make the whole torus compact. You could use a very steep radial power law distribution. And you can change those numbers of clouds along the line of sight and still get the same thing. So there is a lot of degeneracy there. As I pointed out with the example of NGC 2110, we have a problem with some kinds of dust composition, and we just really haven't explored that yet. A difficulty on the observational side for us thinking about CanariCam observations, where we obviously do want to continue this kind of work, is the limited spectral coverage. And so we do want to combine not only these sorts of N-band spectral measurements, but using some photometric points elsewhere as well. And so the big outstanding question that we're trying to answer collectively is whether these dusty tori of type 1 and 2 AGN are really different. For example, there may be some differences in the total number of clouds there. And so this is something that Los Piratas are really aiming to get at, not only with some planned guarantee time that we have, but expanding into a larger ESO program led by Almudena. And so I hope that we'll come up with some better systematic answers for those kinds of questions.
Thank you, Nancy. Just time for one or two quick questions. Jose Miguel, I saw you first.
Nancy, given that the clouds that you have in the torus should be participating of the overall motion of the
yes.
torus, you could find epochs.
Yes.
You could see the silicate emission and later in absorption or variability in general.
So the first general point, absolutely you would expect variability. And the most sensitive observations to that kind of variability really are the X-ray measurements that are directly telling you about line-of-sight column density. But it turns out the silicate emission isn't so sensitive to that because the silicate depends on the total distribution of the clouds. And so moving one more cloud in or out of the line of sight doesn't affect globally what's happening. So we would expect to have much less sensitivity to that kind of small scale of variation in the mid-IR.
The best way to look at that problem maybe is with X-ray
yes.
observation. X-ray definitely will show this variation between type 1
and Nancy, I think the top bullet point on your last slide is particularly appropriate because with these models there are so many parameters, and although I am not suggesting that a homogeneous torus is appropriate because they're dynamically not stable anyway, but nonetheless you can get a good fit with a homogeneous torus. So if you add, for example, on 1068, some hot dust in the narrow line region, you can get a reasonably good fit. So sorry, if you want to answer that.
Yeah. So yes, you can get a good fit, but what I think the big problem for the smooth torus is yes, you can rearrange the parameters of the smooth torus for any particular case, but then you wind up having very particular and very different answers for different AGN. as opposed to collectively having a similar
you have
picture.
different numbers of clumps for different AGNs. But I'm not suggesting it is a homogeneous torus. I'm just supporting your point that these models have a huge number of parameters. But also, you know, how in the mid-IR are you actually going to distinguish the contribution from emission and absorption? Because that seems to me a major problem, and I wonder, you know, whether that's part of your problem in determining the nature of the dust, because I would be surprised if it was unusual type of dust in these torus.
Let's see. So I guess I'm not. So I'm not sure I'm really understanding the question about distinguishing between emission and absorption. That we know that in the beam, the reality, even with great resolution, it's still essentially taking in the whole torus.
Sure. So you distinguish the amount of emission and absorption because of your model fit, or do you not attempt? I mean, how?
So it's not that I would turn around and say I have X amount of emission plus Y amount of absorption. Instead I've already added all of that together to produce a single spectrum.
Okay, but so your final spectrum is a composition
of
some emission and some absorption.
Right.
But the relative amount is hugely model dependent.
Exactly, and those sorts of parameters, like the number of clouds,
is fraught with difficulty in using the mid-IR spectrum.
Yes, exactly. You have to use some kind of model decomposition to pull that back out. Absolutely, because you don't get it directly. Yeah.
Well, you can. There's one way you can do it.
Oh, wait. What's the key? What's it? Right. Exactly.
Let me suggest there's a couple of questions to Nancy. We're about 10 minutes behind on coffee. So let me suggest to the people who want to ask questions to come and talk to Nancy during the coffee break. I'm sorry to cut off there a little bit early. So let us say thanks to Nancy and also the speakers in this session again.
And we resume here at what time?
So we'll start again. Shall we start a little bit later, Jose Miguel, than is on here? Say 11:30? Okay, 11:30.